All right, ready to dive into some seriously cool machine learning research? Today we're taking on Bayesian graph traversal, a paper that grapples with a problem you find everywhere. From robotics to, well, figuring out the best route for a road trip.
Yeah, it's all about making smart choices when you're moving through a network, but you don't know all the costs and benefits up front. Like, imagine you're exploring a new city. You want to hit all the best spots, but you don't know where they are, and wandering around aimlessly gets expensive.
Exactly. You have to balance exploring new areas with exploiting what you already know, and that's where the Bayesian part comes in. They use this clever approach with Gaussian processes. Think of them as fancy ways to estimate those unknown rewards and costs, and how sure you are about those estimates.
Right, like you might start with a rough idea of how good a restaurant is based on online reviews, but as you eat there and talk to people, your opinion gets more refined. Same idea here.
Love that analogy.
Yeah.
So we have this graph, which is just a bunch of points connected by lines. Some points give you a reward when you visit think information, resources, whatever. The connections or edges cost you something to travel a long time, energy, you name it. The catch is you don't know these rewards and costs beforehand. You have to figure them out as you go.
And that's where the exploration-exploitation dilemma really kicks in. Do you stick with what you think you know, or venture out into the unknown, risking higher costs now for potential bigger gains later?
So for our listeners who want to understand how these clever algorithms work, this deep dive is your shortcut to the core ideas. We're going to break down how this Bayesian traveler, as the paper calls it, navigates this uncertain graph, balancing learning with maximizing its rewards. No need to get bogged down in the math.
The paper does a great job of laying out the problem step by step. First, they define it formally, talking about the graph, the unknown rewards and costs, the goal of maximizing the net gain, all that good stuff.
But then they do something really interesting. They take a detour into a hypothetical scenario, imagining a clairvoyant traveler. This traveler knows everything, all the rewards, all the costs. You'd think that would make things easy, right?
Well, not so fast. What they show is that even with perfect information, finding the absolute best path through the graph is still incredibly hard. Like, computationally, it's a nightmare, especially as the network gets larger.
So even if you knew everything, finding the best route is a challenge. That's a really important point to establish.
Yeah. They connect it to this classic computer science problem called the Hamiltonian path problem, which is known to be really tough to solve perfectly. So that sets the stage. Even in the best case scenario, it's not a walk in the park.
Okay, so the difficulty is baked in, even with perfect knowledge. What did they learn by studying this clairvoyant traveler? What insights did they glean?
Well, they were able to prove some pretty interesting properties about optimal paths. For example, they showed that the best path will never repeat the same loop. Like, if you've already visited all the points in a cycle, going around again just adds to your cost without any extra benefit.
Right, that's just wasting resources. Makes perfect sense.
They also found that if you have two paths that end up at the same place, and one of them includes all the points of the other, you'd never choose both in the optimal solution. You'd just pick the one that covers more ground.
So no need to take the scenic route if you can get the same rewards with a more direct path. Efficient.
Exactly. They also looked at those connections in the network that aren't part of any closed loop, like bridges connecting different areas. They proved that these connections will be used at most twice in the best possible path.
Interesting. So you might cross that bridge once to explore a new area, and maybe once more to get back. But that's it.
And for graphs that don't have any loops at all, they found even stricter limitations. Like there's a limit on how many times you can visit each point and a maximum length for the optimal path. All this, even though it's for the perfect information case, gives us clues about what good explorating strategies might look like when we don't know everything.
Yeah, it provides a framework for thinking about efficient exploration. Okay, so now let's get to the real meat of it. The paper then shifts gears to the more realistic scenario. Our traveler doesn't know the rewards and costs. How do they approach this?
They introduce 4 different heuristic policies, basically. These are smart, rule-based strategies that try to find good solutions, even though they might not be perfect. The first one is the myopic baseline policy. Super simple. At each step, the traveler just picks the next point that seems to offer the highest immediate reward based on what it knows so far.
So it's the grab the low-hanging fruit approach. But that might lead to some missed opportunities down the line, right?
Yeah, totally. It's easy to compute, but very short-sighted. Doesn't think about the long game at all. Then we have the upper confidence bound, or UCB policy. This one's a bit more sophisticated. It tries to balance exploration and exploitation.
How so?
Well, it looks at the expected reward of each option, but it also adds a bonus based on how uncertain it is about that reward. So if there's a path that hasn't explored much, it gets a bigger bonus, making it more likely to be chosen, even if the current estimate of the reward isn't the highest.
Okay, so it's like saying, hey, this path might be a hidden gem. Let's check it out just in case.
Exactly. It's all about intelligently managing that uncertainty. Then there's the H-path policy, which takes an even longer view. Instead of just looking at the next step, it considers a whole sequence of H steps.
So it's like planning a few moves in advance.
Precisely. It tries to find the best sequence of moves over that horizon, taking into account both the expected rewards and the potential for reducing uncertainty along the way. It's a more complex calculation, but it can lead to better overall results.
Makes sense. And what's the last policy they looked at?
That's the speculating clairvoyant policy. This one's kind of interesting. It basically pretends that the current estimates of the rewards and costs are the actual truth, and then tries to solve the problem as if it was the clairvoyant traveler.
So it's like saying, okay, let's assume for a moment that we know everything. What would the best plan be? And then it tries to follow that plan.
Yeah, pretty much. Of course, since the perfect information case is so hard to solve exactly, they use some clever algorithms to approximate the solution. And they even add some randomness to the process to help it avoid getting stuck in bad solutions.
Okay, so we have these 4 policies, each with its own strengths and weaknesses. How did they test them out?
They did a bunch of computational experiments, starting with a small, densely connected network just to see how each policy behaves. Well, the myopic and the basic UCB policies performed okay, but they didn't do anything fancy like backtracking. They just kept moving forward. But the H-path and speculating clairvoyant policies did much better, almost as well as the optimal solution you'd get with perfect knowledge. And interestingly, they did sometimes choose to revisit locations, showing that backtracking can actually be really helpful for long-term gains.
Yeah, sometimes you have to retrace your steps to discover something new or to exploit a reward you missed earlier.
Then, to make things more concrete, they applied these policies to a real-world inspired scenario, using drones for public safety. Imagine a drone exploring a dangerous area during a standoff, trying to gather intelligence.
That's a very timely and relevant application.
The results were pretty striking. The H-path policy did all right, but the speculating clairvoyant policy really shined, showing a big improvement in the overall reward. And they found that tuning the parameters of these policies made a huge difference.
Right, so the algorithm itself is important, but knowing how to tweak it for your specific problem is crucial.
Absolutely. Finally, to see how these policies fare in different types of networks, they tested them on randomly generated graphs with varying sizes and levels of connectedness.
A good way to see how robust these strategies are. What did they find?
Well, the UCB policy wasn't always better than the simple myopic one, especially in those denser networks. But both H-path and speculating clairvoyant consistently outperformed the baseline across all the different network structures.
So planning ahead really pays off.
Yeah, looking ahead, considering future rewards and the value of information, it all makes a big difference. But they also found that there wasn't a single best policy that worked perfectly in every situation. It really depends on the specific characteristics of the network.
That makes sense.
Yeah.
It's like you wouldn't use the same navigation strategy in a dense city as you would in a wide open desert.
Exactly. So the takeaway is there's no one-size-fits-all solution. You have to be smart about choosing and tuning your approach based on the problem you're facing.
So much to think about. And the authors also point out a bunch of exciting directions for future research, like how does the initial level of uncertainty affect things? What about using even more powerful machine learning techniques? How do you handle noisy data or even adversarial environments?
Yeah, they really open up a lot of interesting questions.
This has been a really fascinating look at how to make decisions when you're navigating the unknown. It makes you think, how can we apply these ideas in our own lives? When is it okay to just go with your gut? And when should you take a step back and gather more information, even if it costs you something in the short term? Food for thought for all of us.
Absolutely. And for anyone who wants to dive deeper into the technical details, the link to the paper is down below.
Now let's switch gears to our Novel Notions segment, where we brainstorm some cool ideas inspired by this research.
All right, so building on the fact that there's no single best policy, my first novel notion is all about meta-learning. Imagine a system that could, based on some basic information about a new network, tell you which of these Bayesian graph traversal policies is most likely to work well.
Like an AI advisor for exploration.
Exactly. You could train a meta-learning model on tons of different graph traversal problems where you know the best policy for each one. Then, when you encounter a new problem, you feed in some basic info about the network, and the meta model suggests the best strategy.
That would be incredibly useful, especially for things like autonomous robots. They wouldn't have to rely on a fixed strategy that might not be ideal for the environment they're in. They could adapt on the fly.
Exactly. It could revolutionize how we approach exploration in all sorts of complex scenarios. Now, for my second novel notion, I'm thinking about hybrid policies that can dynamically adjust how much they explore and how far ahead they plan.
So instead of having those fixed parameters for look ahead and exploration, they could change them based on what they're learning about the environment.
Right, like if the agent stumbles upon a region that looks really promising but is also very uncertain, it could temporarily increase its exploration or its look ahead to investigate more thoroughly. And if it's in a well-understood area that doesn't seem very rewarding, it could switch to a more exploitative mode.
So it's like having an explorer that can change its strategy on the fly, becoming more cautious in some areas and more adventurous in others.
Exactly. This kind of adaptability could be super valuable, especially in complex, dynamic environments.
Both of these novel notions are really thought-provoking and point towards some exciting possibilities for future research. Of course, they're just ideas at this point, and there's a lot of work to be done to make them a reality.
Of course. But that's the fun part, exploring the unknown and pushing the boundaries of what's possible.
And that's what we're all about here. So to wrap things up, a huge thanks to our listeners for joining us on this deep dive into Bayesian graph traversal. It's been a real pleasure exploring this fascinating topic.
Always a pleasure to be here.
And remember, the journey of discovery never ends. So keep exploring, keep learning, and keep pushing the boundaries of your own knowledge. Until next time.